Are there any questions? No one has any questions. I did have one student in office hours today talking about assignment 2. And I want to warn you about the iterators. Implementing the external iterator conceptually is probably easier, whereas implementing the internal iterator, some people may find confusing at first if they're not used to dealing with lambdas. So that internal iterator may take a long time to figure out how to do it, but once you figure out how to do it, it'll be much simpler than the internal iterator. And the external iterator, the external iterator, it shouldn't take as long to figure out what to do, but doing it will take more time. Well, no questions. Let me get started. So I need to share the screen. While I do that, it would be nice if I can see a few more faces instead of just black squares. I have to. Okay. Now rearranging all the screens again. Okay, that's one. Do we have a TA for this course? No. That would be nice, but we do not. Partly because it's a money issue and partly because it's hard to find someone to has taken the course before and is not working. Okay, so we ended up last time talking about the command. We're in the middle of talking about command. So we'll go back to command pattern. Basically the command is just a way to sort of wrap up calling a function so we can do it later if need be. And the sample command, which is pretty hooky, sort of gives you the basics. We have some object, in this case a counter object, and we want to be able to call increase on that object. And rather than doing it directly ourselves calling increase on it, we're going to create an increase command, pass in the counter object, and then we will call execute on the command object. And the execute method on the command object will then call the increase. So the idea of command is pretty simple. I think the question more becomes, why do we want to do it? And there are a number of different use cases. One is, as I show here, we can have an undo, right? So if we need to support undo, what we can do is we can create a command object for all the operations we want to be able to undo, implement an undo method, and that way, as you're doing operations, you can take those command objects, execute them, and put them on a done stack. And then if you want to undo an operation, you can then pop off the top one from that stack and call undo on it. Right, so that's one use case where we can actually implement undo. Yeah, another use case is when we want to execute things later. And there could be various situations where that happens. One is, like I said last time, we want like a callback method from a button or menu. So we can give the menu a counter button or a counter menu item, our command object, and every time the user selects that button or that menu item, then the menu, the button, all it has to know is call execute on the command. It doesn't have to know what it's actually doing, so we can reuse those buttons or reuse those menu items to execute different types of things. Another use case is we can then create a bunch of command objects and create a little language that we might implement and create a little, then we create a little program using those command objects. And then we'll see that a little later. Does that make sense? Now, the problem with that simple example is there's an obvious undo method. Increase, undo is decreased by 1. Other situations, we may require more information to execute the command. The method we want to execute in the command may require arguments. There may not be a natural inverse like there is an increase and decrease. So we may need to store more information in the command object to actually implement the undo. So when to use it, like I said, one use case is you want an action as a parameter, like a callback method in a button or menu. Depending upon what type of action you need to do, we can now, if the action is simple enough, we can wrap it up in a lambda instead of using an entire object. Another use case, like I said, we can queue them up for requests to be done later. If you want, undo, logging changes, so we can actually create every operation we do, we create a command, and that command will execute whatever operation it's supposed to do, but also then log that operation. One example of this is in-memory databases have become popular, particularly in the finance world, where being as fast as possible becomes important, particularly when you're doing stock, trading stocks. For example, there is a company in Chicago that wasn't, they wanted to get an advantage over their competitors. So they had a fiber optic cable laid from their headquarters in Chicago to the New York Stock Exchange. Why? Well, because since it was just for them, they could route it so it was a little bit shorter than the other routes going from Chicago to New York. So the trades they executed on that on the New York Stock Exchange would get there faster, slightly faster than their competitors in Chicago. And you can imagine laying a fiber optic cable from Chicago to New York is expensive, right? But it was worth it to them to go through that expense just to gain a few milliseconds on their competitors. So it's become common in that environment to store databases in memory. Typically a database like MySQL or Postgres or Oracle, where the data really lies on the disk and it'll cache down the data, but there are times when you make a query that you actually have to wait for the disk or the solid state drive to get the data back into memory. So in an in-memory database, we store all the data in memory because access is much faster, right? Then the problem is as you're changing the data in the database memory, we have to worry about faults. What happens if many people are executing operations on that database in memory and the machine crashes, right? What happens to those operations? So one common solution is what we do is every time we execute an operation in memory database, we do the change in memory, and then we just log the fact that here is a transaction we want to do, right? And then if the machine crashes or we need to reboot, what we do is we start from some known state and then replay all the operations in that log, get back to the current state. So that's another place where we can use the command pattern is for every operation we want to do on that database, we have a command. When we execute the command, it then changes the data in the database and it logs the change, the command that we want to perform on disk at the same time. High-level operations built on primitive operations. One example I know of this, actually I know several examples with kids, teaching kids how to program. So I know several tools where there's different types of operations they can do, and each one has an icon, and they grab the icon and move the screen, and then they can type in, some data related to it, and they keep on grabbing these icons. But each one of these icons really is a command object, and they're building up. Here's a set of command objects in the stack, even though they think of it as a graphic representation. And then when they want to execute the program, we just go through and we just execute each one of those command objects. And usually these things are graphical, so they're moving something on the screen and drawing lines and drawing fancy images. That's another example of when we might want to use the command pattern. The sub use cases, well, if you have a transaction, how do you roll back a transaction, right? In the middle of it, you've executed 5 operations and the 6th operation can't go forward for some reason, so we need to roll it back. Well, if we use the command pattern for all of the each operations in our transaction, we have an easy way to roll back the transaction if each command object implements undo. All right, so these are sort of some common use cases for when we want to use a command pattern. So far, so good. And yeah, macro language, very similar to building high-level operations and primitive operations. Consequences, well, it does add one level of indirection. There is a famous quote in computer science that there's no problem you can't solve by adding another level of indirection. And the corresponding part of it is there's no performance issue you can't solve by removing a level of indirection. And yeah, we can add new commands because we don't have to worry about changing existing ones, existing classes. And we can assemble, we can take command object and put them into composite command object to create a program or a larger operation. Now, one problem which may not become immediately obvious is that except for very complicated cases, commands are very simple, command objects are very simple, and it gets very repetitive implementing commands. The simple commands are structures are very same. You're going to pass in some receiver object to do something, and then you're actually going to call a method on it, and you might need some parameters, but that's probably 80% of all command objects. And you do it over and over again, and by the third or fourth time, you're like, this is boring. I've done this over and over again, and it's always the same thing. It's just that the class of receiver is different. The name of the method we're going to execute is different. So then you want to start asking, is there any way we can automate building these commands? And so this is where the idea of pluggable commands comes in, to create one sort of general command, which we can configure saying, oh, here's the object you're going to call on, here's the name of the method you're going to call, and here's the list of arguments. And so we can use the same command object over and over again in different situations, rather than having to create each command object from scratch each time and repeat the same process over and over again. Prior to lambdas, in Java, doing this sort of complicated. Here's an instance of doing that where my receiver, since I don't know the exact type of the receiver is going to be yet, we can make an object because that's sort of the parent class of all classes in Java. I need to know what method I want to call on the receiver, and so it has to be a type method, and then we need to know which arguments are going to be needed for the method we're going to call. And the actual calling of the operation is fairly straightforward. We can call invoke on an object, and we have to pass in the receiver. And the arguments. In Java, the problem is all of a sudden we get these exceptions raised, which normally we wouldn't, which we then have to deal with outside the command. And using it, you know, it's a bit complicated because, you know, we need, you know, here's object I'm going to call on. Here, so I get the, you know, the method out of that I want to call. And the arguments need a special type. And once I've done that, we can use this command, in this case, to add an element to a vector. Any questions so far? No questions. I must admit there are times when I am prompted or tempted to use this one trick I once learned. I came across, you know, a professor who said, at the beginning of every class, I tell students that I'm going to make one mistake in every lecture. And your job is to discover the mistake. Of course, you know, once we've got lambdas, we can now simplify this by passing in lambdas that we want to operate on. And in Java, we need to create a type. And so for lambdas, the type has to be an interface with only one operation. And then here is an example of using that improved version where I create a counter object, I create my pluggable command, and now I pass in two lambdas, one to call increase on the counter and one to call decrease. But again, as the situation gets more and more complicated, it becomes harder and harder to use lambdas.
Sorry, could you what did you say about lambda's restrictions? Or
well, there's several things. One is lambdas make it harder to complicated things. You know, one is, you know, say I need doing increase and decrease is an obvious inverse, right? But what happens if I'm inserting text into a text, you know, a string, right? To undo that, I need to know what text was added and where it was added and what it replaced. So when I do my execute, I need to store that information, right? So that when I undo, I can access it. Using lambdas like this, I can't do that. And there's also Java lambdas make it harder to do certain things. But again, the main idea is that, once you start building command objects or classes, they're all basically the same except for the more complicated ones. And it gets to be very repetitive very quickly. And so programmers tend to like to avoid doing work by being clever. Depending upon your language and the functionality lambdas give you, they can replace using the command objects in some situations directly. And it's someone said it seemed confusing, but for me, it's basically the same idea. The idea of a command object is that we need to decouple calling that method directly so we can do it either later, we can do additional operations on it. And lambdas allow us to achieve the same thing in many circumstances. So for me, the question becomes, what's the objective? And what tools do we have to achieve that objective? In a language like Java, prior to lambdas, we only had the command objects and classes to do it. With lambdas, now we can simplify it by using lambda in many cases. And I've actually come across at least one person trying to say, well, we can actually, being clever with lambdas, we can get the same behavior as a class, so we can view a class as sort of a special purpose lambda. I'm not sure I go that far, but if you're, people like to have language wars, in this case, wars between functional programming and object programming, and so in functional programming, yeah, we can just use a function, right? But the function needs a receiver and state. What do we do? Well, again, depending upon your language, some closures will also do that. Here's a simple closure where I've got a local variable and I'm returning a lambda, which increases the value of n by 1. And this language result is returned. So I'm creating 2 counters, and then I can, when I call counter A, it increases the value by n by 1. And when I call it again, we get 2. Right, so the lambdas we're dealing with do have state that they can operate on just like an object. Let that sink in for a little bit, see if anyone has an objection, a complaint.
Maybe I'm missing something, but you're declaring n equals 0 at the top of the counter.
Yes.
So wouldn't that always return 1?
N is a local variable, right? This lambda has a reference to it. It's also a closure, so it keeps track of that. And this, right, in the C-like languages, plus equals means increment that variable by 1. So what's happening here is that lambda will increase its copy of n by 1 each time you call it. Does that answer your?
Yeah, I think I got it now.
Yeah. Yeah, again, I never know how much experience students have had with lambdas and closures. They've been around forever. They first appeared in Lisp, which was, I think Lisp was started in the 1950s, early 60s. So it's been around for at least 60 years now. They're heavily used in Smalltalk, which came out in the early 80s. But they didn't seem to hit mainstream languages until recently. They're extremely useful and powerful. So, example where we can, lambdas can encapsulate state. So they can do more than you might think initially. They can maintain state. Here, I'm returning 2 lambdas, and each of those lambdas are going to share, right, the state. And so I can do more complicated things. I can have 2 lambdas that share the same state, and they can then operate on that shared state. Again, a slight pause to make sure everyone is with me.
So I haven't seen something like this before, but it makes some amount of sense to me. How intimately are we going to need to know this particular concept?
You probably won't need it in this class, but if you graduate with a master's degree in computer science in 2020 or later, this should not be a concept you haven't seen before, right? Functional programming is growing by the day. Its influence is growing by the day. Seen by the fact that, several years ago in Java 8, Java added lambdas and closures. Most of the newer languages have better implementations of lambdas and closures and use them more extensively than Java. But I think you'll have a hard time finding a language that came out in the last 10 years that does not have lambdas closures implemented. And and used extensively. And things like, Spark, using lambdas is essential. I mean, you can't do anything in Spark without using lambdas. Just so in terms of the course, you probably don't need it, but for your future career, you should know about it.
Okay.
Any other questions?
I have a question. This is the first time I hear that functions can keep state. And I guess my question is, where is this saved? Like, is this something that gets then allocated dynamically and goes into the heap, or is it in the stack? And how does changing like context work with this?
Yeah, sure. Okay. Implementing closures like this is not an easy process, right? Because you have to capture your local environment. Here, the local environment is just this one value, but the local environment could be larger than that. And you then have to capture it, right? That is a complicated process. Some languages don't do it very well, or they instead of going all out, they say, well, it's doing everything is really hard, and so we're going to do this, just a small piece. But yeah, it can be tricky. And I know, I forget which language it is, but you have to mark every variable in the outside world that you want the lambda to capture, especially, just to help the compiler out. But yeah, it's I don't think they're gonna do it in the stack because that's gonna be very hard. So I assume it's on the heap, but I don't, that I haven't. And I always tell students, look, when you first see lambdas and closures and you don't think about it, it's like, okay, yeah, sure, no problem. But then we start thinking about it, it's like you did, like, huh? I mean, where is that n being stored? How does it actually operate? Then it becomes confusing. Any other questions I can skip over, avoid? Yeah, and there's various ways we can do this in functional world. This is Julia. I think we can skip this because it becomes more and more convoluted if you don't understand Julia. That's, like I said, the command pattern is fairly straightforward. Now what I wanted to do is I'm going to go back to look at some things that skipped over from the observer. Again, more material that you're not really going to use in this course, but it's also related to this trend in functional programming that you should see if you're a graduate student, and you don't want to, but you know it exists. So let me go back to observer pattern and we talked about reactive programming. Yeah, so I want to go back to document 7, slide 32, if you're following along. And I'm going to talk a little bit about reactive programming. And so you can all relax now. I'm not going to ask you this on exam. I don't plan on giving you assignments on this. This is like general education, right? To make you up to date a little bit. Reactive programming, like I said, is becoming popular. Both Android and iOS now they're both Google and Apple are implementing, making their system to build apps use reactive programming concepts. Flutter does this. A lot of the web frameworks now have this sort of reactive programming. And there's sort of two big ideas. You know, one is there are a lot of things we deal with which seem different. I have objects and they change their values. We have a collection and we may add things to collections, delete things from collections. We've got events, people click on buttons, they swipe, click on menus. There's all these events that occur in programs. We do network calls, right? And then we get responses back later. We have all this asynchronous stuff. And most of the time, all these things appear to be different and we treat them as different. We handle each one differently. So one of the ideas is they're trying to take these ideas of events and collections and changing values and objects and asynchronous callbacks so we can handle them the same way. So we've got one mechanism to deal with all of them instead of different ways of doing each one. Right, so that's one big concept they use. Another one is one-way data flows. How to explain this? Look, normally what we do is when we build a program, right, we've got data and we will then, user does something, and so we have to modify the data, and once the data changes, we then need to update a bunch of other stuff, right? And so we start writing code where we grab things from the screen, from the text field, we update it here, and since we updated it here, we better save it to a file, and then we need to, that value is also used over here, so we need to update this part of the screen. And so every time we do something, we are interacting with the data, we're updating data, and the data, and based upon that, we then have to update other things too. And that gets complicated because now every change involves changing the data, then updating a bunch of other stuff, right? And now this change updates this data and other things. So every time we add another way of changing things, it involves knowing the data and all the things you have to update because that data changed, all right? And so every time we have a way of modifying our data, we also have to know where that data is used, right? So what they want to do is say, look, no, that gets too complicated. Things get too tangled up. So you can have data here, and if you want to change your data, you change it. That's it. You change the data, and you do not then go update all over the place. What you do is then all these places that depend upon this value, will register themselves as being dependent on that data. So when you want to change it, the user types in a value in this text field, you pull out the text field, modify the data, you're done. The data will then broadcast this change to all the places that need to be updated. And that's going to greatly simplify it, because now every time you need to change data, you just change the data. You don't have to go and say, oh yeah, piece of data is used in 5 different places, because those 5 different places will now register themselves to be interested in that piece of data. So are these 2 ideas clear, or somewhat clear? So this is, sort of the goal of reactive programming, to implement these 2 ideas. So the way to think about this unifying data types, say I've got a collection, I'm going to iterate over the collection, right? And I'm going to do something in each collection. We can then, on a timeline, sort of mark, right, each time an element gets modified. Now, if the process each element executes the same time each time for each element, then we get a timeline that looks like this. But if different elements take longer to process for some reason, we may get a timeline like this, right? The first element gets modified, but the second one takes much longer time, and so it gets done here. The third one is pretty short. The fourth one takes more time, right? So when we look at when those values get changed or modified or processed, it looks like this. We've got a class with, with a field in it, in this case bar. Again, over time, we're going to modify that value. And depending on what we do, we might get a timeline looks like this, right? So the timelines look the same, right? There's an event where a value gets changed. Some time passes, another value gets changed. So going through a collection, right? Iterating through a collection, you think it as, again, we're having events happen or things changing over time. We're changing the values of a field, changing over time. You've got events occurring. Again, you got these events occurring over time. So they start looking at your program as just things that happen over time. And how can we then capture those events the same way? And so they talk about subjects, or if we use a terminology from the observer pattern, observables, they're going to generate a stream or flow of events or data over time. Now that stream could be just every time the value changes. That stream could be events generated by people clicking on the screen or clicking on buttons. Or could be, iterating through a collection. So we get these subjects encapsulate all those operations. And so if that's all they do, it's basically like a observer, subject observer from the observer pattern. But these streams also support, map and filter and various other operations, so that we can now, when we get these stream events, we can use them to transform them to something else if we want to. And then they send 3 types of messages. One is on next, that is, okay, another thing happened, here's the value. And that value could be the next thing in a collection. That value could be the data you got from the network call, or it could be someone press on a button. On completed, the stream is done. We've gone through all the elements in a collection. We've closed down the network connection, or an error occurred. Now, there's different types of streams. And some streams will give all the events from the very beginning. Some streams or subjects will only give events or data that occurs from now into the future. And some allow subjects to say, look, you're going too fast. I can't keep up, slow down. Look at an example. Well, it's an RX Java. And remember, RX stands for this reactive library that came out to Microsoft a number of years ago. And it exists, so of course, in C# and in Java now, and Python and Swift and other languages. So Flowable allows clients or observers to tell the stream to slow down. Observable, no, same as slow, we can't tell it to slow down. So a bunch of different types of subjects. So some very simple examples. Now here's the whole world of RX programming. I'm creating a flowable. It's going to create a stream of values, but it's just, which means it only has one value. And then various things can subscribe to that value. And so I only have one subscriber. And I pass in a lambda to tell it what to do. In this case, I'm telling it to print out. Now it's clearly a convoluted way to print out hello world. So let's look at a slightly more complicated example. Well, subscribe method, we've got 3 versions. What to do when we get on next message, what to do when we get on next or on an error, what to do on next, on air, and when the stream is done. And for consumers in Java, we basically, the lambda gets one argument, that is the value, and no return. Here's a slightly more complicated example. I'm creating a flowable on a range from 1 to 5, and then I'm attaching a map to it to square it, and a filter to only select out the even values. And then, keep track of what's going on. I have a print statement. I now subscribe to the flow just to print out the values. And I then subscribe a second time. And so what's happening is, right, when I get my start, and then I subscribe, and my first subscribe says print things out. And so it's going to get the values from the flow. And so we need all the squares which are even. So I get 4 and 16. Print out second again, and now I subscribe again, and the second subscription is going to get the same values as the first. Again, now a slight pause for people to ponder, think about it.
So does this then flow twice? Or is it taking the output of one flow and using it twice?
It's taking the output of a flow and using it twice, yes.
How is this example? So is that the way in this feels like this flowable is kind of just like an iterator
Yes.
in this case.
You can think of a flow as an iterator, but with some special features. One is we can add map and filter and et cetera to it, right? Which you can't do on a regular iterator. You have to do it separately, right? The second feature is we can have multiple listeners or multiple subscribers to that same flow, which you cannot do to an iterator, right? And the third difference is, right, I'm using a very simple flowable here, just as an example, but the flowable could be anything, right? It could be, again, network calls. It could be a collection. It could be events happening, right? It could be people changing values on a field. Now, how can this be useful? Again, remember I talked about having one-way flows, so we have some data, and a piece of data may be displayed in multiple locations for different reasons. We can then create a flow on the piece of data and have each place we want to display it, right, as a subscriber. So now when I change the value of that data, right, there's one flow coming out, but there are multiple subscribers, and they'll be updated. So we don't have to worry about, oh, I changed value X, so now go update here and update here and update there. Does it sort of make sense?
Yeah, I think so.
I mean, so this level, right, is just fixed number of events. Creating things which have variable number of data points. We can use emitters and subjects. And again, they do the on complete and error and on next. So here I'm creating an observable on an emitter, and then I'm sending several messages to it, and then I have a subscriber to it. So it is possible to have these observables or flows on dynamic systems. You know, a slightly more complicated example, where, you know, I'm just iterating through, and every so often I create an event to sort of simulate a long-running process, or listening to a button, or listening to network calls. But again, we get something that creates a flow that we can observe, and we have subscribers to it to observe it. And we have multiple subscribers, and we can also have, you know, map and filter on it. Right, so just again, I'm just having simple examples to sort of give you some ideas. So subjects are both observable and observers, so they can read events and they can pass events on. And there's different types. Right, so here is, I'm creating a subject, and I create a subscriber to it. And what I'm doing is, right, new values are printed out. If I get an exception, I print it out to get a stack trace. And when we're all done, I print out done. And right, then I can send a message to my subject, start, and do A. I can subscribe again. So now I've got 2 subscribers to the same flow. And then I can send more messages to my subject, and then I call complete. And here's the output I get. You know, so I get, you know, my start, and then I get A. And then I subscribe again. And this particular subject, you only get the new events, you don't get the old elements of the flow. And so now I get the B from the first subscriber, and then later B from the second subscriber. Right. And then I pass on C. And so I get both C's. And then when I say your subject is done or completed, right, my first subscriber, since it has that lambda to print out done, I get done. The second subscriber only to tell me what to do when I get a new value. So now while you think about this, I need to tell you a story. When I was a graduate student, which was, you know, a long, long time ago now, my graduate advisor had lots of money, so he bought a special purpose machine to run APL, or a programming language, which you've probably never heard of. It was a very interesting language. It was a vector-based language. And so all the operations in the language operate on vectors or matrices. And so the way you wrote programs in APL was completely different than you would in C or any other language you know. Plus, you use a special keyboard at the time because all the operations were sort of mathematical operations. And so you had, you know, delta was a operation in the language, and there was a row and all kinds of things. And so it was a standalone machine, and like I could access this. Okay, let's just try it out. So I thought, okay, since I'm, you know, working for him and I'm doing his grading, let's write a grader program to keep track of grades on this machine. And so I started out, and at the time, the language everyone used in education was Pascal. And so I was like, okay. And I got partway through writing this program, and I realized, no, what I'm doing is I'm writing the language, I'm writing the program in Pascal in my head, and then I'm converting it into APL. And so what I'm getting is a Pascal program written in APL, and this is not good because the two languages operate completely differently. And if you're going to write a program in APL and Pascal, just write it in Pascal, because you do it in APL, it's a mess. And so then I said, okay, that's no problem. So I erased that first version. I started version 2. And again, partway through version 2, it's like, well, you know, it still looks a lot like Pascal, not as bad as my first version. So then I threw away version 2 and started version 3. And again, at some point I go, well, you know, it's looking more like APL, but there's still an awful lot of Pascal in here. So I'll throw away version 3. And it was only until I got to version 5 that I say, well, you know, I think I might start to understand how to write a program in APL. It would have really taken me finishing that program and writing a bunch of other programs to really bend my head around how you write programs in APL. Now, of course, APL didn't go very far because, as many people said, APL was a write once, read never, because it's impossible to read a program once you implement it in APL, because, I mean, literally, well, does anyone know Conway's Game of Life, where you have these cells and they grow and shrink and create patterns? Anyone familiar with that?
Kind of.
In APL, that's a one-line program. And once you've written it, someone else will never understand what it does. I mean, they have no idea. But the point is, when you start writing programs in a new paradigm, the farther away that paradigm is from what you're used to, the longer it takes and harder it is to understand how to restructure the program to fit that paradigm. Using Java RX, we can do simple things with it, but eventually you'll realize that writing programs fully utilizing reactive programming means we have to rethink how we structure programs and put them together, right? And that's not going to happen, you know, by me giving you, you know, a 20-minute lecture on RX Java. And it's like I said, you know, in the iOS world, Swift UI is doing this. Android is coming out with what they call Compose. Flutter uses reactive programming. So the way you put together applications using those systems is different than you would normally. So it does take some time to understand how to write programs in that paradigm. And most of you will in the future come across systems doing using reactive features. Okay, any questions? Our world is, the world of software development is changing. It changes all the time. People like to think it changes quite rapidly, but things do take a long time to go from experimental to accepted to mainstream. But these changes are coming, and you should be aware of them and be ready for them. So next time I want to talk about the visitor pattern. You should try reading a visitor pattern before class, and then we'll talk about in class, and then maybe you'll read it again after class. Visitor pattern does some weird things. And after visitor pattern, we'll talk about some more simple patterns. Well, we're out of time. Hope you have a good weekend, and I will see people on Tuesday.
Have a good night.